In this video we will take a look at the von Neumann architecture. So before 1945, computers were essentially machines that had been pre-programmed to perform a particular task. So you would have a computer, you would set up its wires and its switches, it would perform a task. So if you wanted a machine to do another task, you would actually have to set it up slightly differently. And in that way, the program was considered to be part of the machine. The only thing that you would actually give it was data to process. Now, John von Neumann, a famous mathematician, in 1945, he wondered whether it would be possible to create a computer where the program and the data were actually separate, they were independent of the machine. So the idea would be that you would have one multi-purpose computer and you could supply it with different programs and different data, and that one computer could perform lots and lots of different tasks without having to be set up any differently. Now, he invented the von Neumann architecture. So this is effectively the modern day CPU that we have, and in this type of architecture, the data and the instructions are held together in memory. They're fetched, decoded and executed one at a time. So what it means is that simple programs, they could be written containing both instructions and data, and they could be executed by the computer without having to change the setup of the machine. And it wasn't long after that computer scientists, they invented coding languages so that programming software was accessible to many, many different people. Now, the von Neumann architecture works by following instructions from effectively assembly language. So all von Neumann CPUs, they've got an instruction set. By saying that, it means that there's a list of instructions that the CPU knows how to execute. And there's very, very few of them. Here's just a small number of, a fairly small number of instructions. And you can see here that the instruction add means add numbers together. Sub means subtract numbers from each other. STA means store a value in the accumulator. You've got LDA, which means load a value into the accumulator. We've got BRA, which means branch to a different part of the program, and out is output of value after it's been processed. There are a few other instructions, but these are the main ones that we will deal with today. So a CPU can perform each of these instructions, and there's some really, really important parts of the von Neumann architecture that we need to be aware of. And these different parts, they're registers, and they will perform, their own very important tasks during the Fetch-Decode-Execute cycle, and we'll have a look at those. Now, the really important registers that you need to know about, and remember that a register is just a small memory location. The first one is the accumulator. There's the program counter, there's the memory address register, the instruction register, the memory data register. Now, it's probably quite scary hearing these maybe for the first time, but in an example, we hopefully will understand their purpose. So let's take a look at an example program and how the von Neumann architecture deals with the instructions and the data. So you can see here in this example program, which is a visualization of how the data might be loaded in RAM, we've got different addresses, address 00, 01 and 02, each of those containing an instruction. In address 04 and 05, we've got the contents, which is data, the number 5 and the number 2. So how this program, or what this program actually means, if we look at the first instruction, that means load to the accumulator the contents of address 4. And you can see in address 4 that that is the number 5, the integer 5. So 5 would first of all be loaded to the accumulator. Then the second instruction, which is sub 5, that means subtract from the accumulator the contents of address 5, and you can see that the integer 2 is in address 5, so the number 2 would be taken away from whatever's in the accumulator. And then finally, address 2 has got the instruction store the value from the accumulator into address 6, so whatever has just been stored as an output into the accumulator from that calculation, which would be the number 3, because 5 take away 2 is 3, would then be put into address 6, so stored back into RAM. So let's have a look to see how these different registers, what their role is during the Fetch-Decode-Execute cycle as we work through this program. So first of all, we've got the fetch cycle. So the program counter will start off at 0. That means that we effectively are on our first cycle, and because of that we need to look in the first address. So the 0 would be copied from the program counter to the memory address register. In other words, we want to have a look in address 0 first of all. So the CPU would then send a request for the data in address 0 by sending that address along the address bus to the RAM. The RAM would then respond by sending the instruction LDA4 back to the CPU, and that is then stored in the memory data register. Now, because it is an instruction that's been sent back, that needs to be decoded, so it's moved into the instruction register so it can be decoded. So now we've got an instruction in the instruction register. The CPU will look up what that instruction means in its instruction set, and it can have a look to see that LDA means load a value into the accumulator. So load the contents of address 4 into the accumulator. So now the CPU understands what that means. It's decoded it. So now it's ready to execute that instruction. So the CPU will do exactly that. It will load the contents of address 4 into the accumulator. So it goes back to the RAM and it gets the data that is in address 4, which is the number 5, and that is put into the accumulator like so. The program counter increments on to 1, and that's the end of the first fetch, decode, execute cycle. So 5 has been put into the accumulator. We've effectively loaded the data from address 4. So now let's have a look to see the second fetch, decode, execute cycle. So because the program counter is now 1, that value is passed into the memory address register, so the CPU knows to look in the address 01. So it sends a request to the RAM for the data in address 01, and it passes that request along the address bus. The RAM responds by sending back the instruction in address 1, which is sub 5, back to the memory data register. And again, because it's an instruction, that is moved into the instruction register. It is then decoded, so it's looked up in its instruction set. It understands what sub 5 means, and it means subtract the contents of address 5 from the accumulator. So it understands what to do. It's now ready to do it. So in address 5 in the RAM, we have got the number 2. So 2 is taken away from the contents of the accumulator, which was 5, to produce 3. So 3 is now the contents of the accumulator. And that is the end of the second fetch, decode, execute cycle. Now, if we were to go and try and finish this off, we would increment the program counter, or the CPU would increment the program counter by 1, so it becomes 2. 2 would go into the memory address register. The CPU would then request the instruction or data that is in address 2, and it would send that request along the address bus. STA6 is the instruction that is in address 2, so that is then sent back to the CPU along the data bus. Because it's an instruction, it's going to be moved into the instruction register where it will be decoded, and the CPU would then realize that STA6 means store the value that's in the accumulator back into address 6. So the value 3, the number 3, would be taken from the accumulator and stored in address 6. And that's how the von Neumann architecture works.